Okay, it's time to start, I guess. So it's really a great pleasure to welcome my dear colleague and friend, Dragana Popovic. She's, responsible for making my long stays in Tallahassee kind of pleasant. We had a lot of nice dinners at your place, right? When you go there. But other than that, it's also homecoming for her. So she is our alum from Brown. So we are proud to see, how far they got, and look at all these grants that she still gets there from NSF. So Dragana actually completed her undergraduate study in Belgrade, University of Belgrade, and then they came here together with her husband, who's a theorist, to Brown. And after Brown, you had very successful career in academia. First, she was a postdoc at IBM. So she worked with another colleague of ours, Zaslavsky. For those of you in condensed matter, you must know Alex. So you were buddies as a postdoc, right? And after that, she was a faculty position at City College of New York. Isn't that where Antal graduated from?
Yes.
Yes, our colleague Antal Levitsky. So you see, we're all connected. And she then, two-body problem, moved to Florida to National High Magnetic Field Lab, Florida State. And she's been there ever since for more than 20 years. So we are, I think this summer, even though we did work in different areas, but we somehow ended up seeing each other on everywhere I went. You were there. So we were in a 2-week conferences in Europe, like everywhere I went, Dragana was there, we were seeing each other. So thank you, and I'm really looking forward for your talk. Thanks for coming and suffering all the government shutdown and problems with the delayed flights. So happy to see you and looking forward to your talk.
Thank you very much. Thank you for the introduction, for the invitation. It's really a great pleasure to be here. As she said, yes.
Apologize for interrupting. I forgot. For those of you who are taking 2010 and suffering in the hardest experiment, quantum oscillation, you can blame her and her advisor for it, okay?
Okay, yeah. I did not take that one when I was a graduate student. So she said, this is a very special occasion for me because Brown is my alma mater, so being here brings back a lot of memories, mostly good ones. And I'm also happy to see that some of the professors that I had as a graduate student are still here. So it's really, I'm very grateful for this opportunity. So I'm an experimental condensed matter physicist, and my general area of research has been so-called strongly correlated materials. In the last almost 20 years, we have been doing a lot of work on high-temperature superconductivity in cuprates and other materials. But my talk today will be on a somewhat different topic that is inherently interdisciplinary, which is why I think it is of interest to a broader audience. And in particular, Okay. So our own work in this area really lies at the intersection of quantum condensed matter physics, quantum statistical physics, and quantum information science. And the fun fact is that this work naturally evolved from my PhD work here at Brown. At this point, I would also like to acknowledge the National Science Foundation for supporting this line of research in our group for many years. So in the first part of the talk, I would like to tell you why non-equilibrium phenomena are important, interesting, and also challenging to study. I also will give why does this keep happening? Okay, I don't know. Okay, yeah. Okay, so I will also introduce two types of non-equilibrium behaviors that are of relevance to us. One of them is glassiness, which is probably the best known type of non-equilibrium behavior. And the other one is the so-called many-body localization, which emerged in the recent years. Okay, I don't know what to do to stop this from happening. which emerged in recent years in the studies of a really fundamental question about how quantum many-body systems thermalize or approach thermal equilibrium in case when they are isolated thermally from the environment. So in the second part of the talk, I will also point out what the important questions are. And in the second part of the talk, I will show you how we addressed some of those questions using a relatively simple model system. I don't know where to point, actually. There, maybe. Simple model system, which is a 2D electron system, where electrons interact, obviously, via Coulomb interaction, and they also move in the presence of a random potential or disorder, which is usually due to impurities or defects in the material. So to study the non-equilibrium properties, in other words, the time-dependent behavior, we measured time-resolved conductivity, because this is what we do mostly. We measure electrical transport. And we use different protocols which are designed to probe both the response of the system to an external perturbation and the evolution of correlations with time. And in this talk, I'm going to have time only to discuss one particular protocol where we measure the response of the system to a perturbation. And you will see that depending on the range of the interaction, the dynamics of the same system can be very different. It can be either glassy or it can exhibit this many-body localization. And at the end of the talk, I will give you a brief, I will give a brief summary or mention briefly some ongoing work and also outline some, we think, exciting directions for future research. Okay, so in condensed matter physics, why are we interested in non-equilibrium properties? Well, it turns out that some complex behaviors of solid-state materials are actually manifestations of far from equilibrium behavior. For example, in the so-called quantum materials, they are characterized by the presence of many competing degrees of freedom, many competing energy scales. So this gives rise to various complex behavior, including the emergence of metastable states, breaking of ergodicity, and the associated non-equilibrium dynamics. And from a practical point of view, there is actually a lot of effort to try to access and control some of these metastable states, because they have properties that are unattainable in equilibrium, and to use these properties for applications. But our focus is really on some fundamental questions, not on applications. So the reason why this is a difficult problem is because we don't have a standard accepted theoretical framework for describing systems that are far from equilibrium. So this is why this remains a grand challenge for condensed matter physics, but also it is a topic of broader significance, because most systems in nature are far from equilibrium, and many phenomena in nature can exist only under far from equilibrium conditions. And this includes, for example, clustering of matter in galaxies, to various types of turbulence on the Earth, such as hurricanes, then avalanches, earthquakes, growth of snowflakes, all the way down to the molecular processes that form the basis of life. So these are all far from equilibrium phenomena. And as I already mentioned, they are important for industrial applications. For example, many processes in industry depend on transport, handling of granular matter. For example, powders and pills in pharmaceutical industry, then seeds, grains, fertilizer pellets in agriculture, and so on. So it is important to understand their inherently far from equilibrium behavior to be able to control that. So the far from equilibrium behavior is ubiquitous. So why and how do systems reach the far from equilibrium regime? Well, one way is if you keep supplying them with energy. For example, you can apply an electric field to a material, or we try to keep ourselves far from thermal equilibrium by, ingesting energy, we eat and drink. But another way, there are some systems that even if you remove this external source of energy, they remain trapped in some states that are far from equilibrium, because the thermal energy supplied by the surroundings is not sufficient it is too small for them to reach thermal equilibrium on experimental timescales. So as a result, such systems retain a memory of the preparation conditions. So both types of systems have been of great interest in research. Our own research has focused mostly on these systems that remain trapped far from equilibrium. And the best known example of that are glasses. So glass, such as structural glass, we don't have any windows here. Window glass, everybody is familiar with that. So basically, these are liquids, that, liquids, so when you cool them down very fast, they are unable to reach the lowest energy state, which is a periodic arrangement of atoms in a crystal lattice, but instead they remain stuck for a long time in some metastable state, in some random configuration. And this figure here actually shows, so in other words, as we cool them down quickly, it's more difficult for them to move, to flow. The viscosity grows, and here we have a figure for several different glass-forming liquids where viscosity is shown on a log scale. You can see as you reduce the temperature, the viscosity increases by 14 or 15 orders of magnitude. So it's really huge. So they, as you know, they look like solids, but if you look at them, they resemble a liquid. There is no periodic arrangement of atoms. So, I mean, liquids should flow, but, it doesn't seem that they flow at room temperature. So, a long time ago, actually almost 100 years ago, 1927, there was a professor Parnell at University of Queensland in Australia who wanted to see whether this kind of material can actually flow. So he used a piece of pitch, and you can see at room temperature, this is solid, it's even brittle, you can shatter it with a hammer. So what he did, he melted this piece of pitch, he poured it into a glass funnel with a sealed stem, and then, he let it cool down, settle. He waited for 3 years, and then he cut the stem to see if it would flow. And then he, waited and waited and waited. And, 8 years later, the first drop fell. Another 8 years later, a second drop fell. I think after 7 drops, they published a paper. And then, maybe this will wake up. Okay. Right, so you can see that so far 9 drops have fallen, the last one 2014. So it seems like it's time for the 10th one to fall. Another fun fact is nobody has actually seen a drop fall. But maybe, you could be a first person to do that if you go to this website, the 10th Watch, and I checked it last Friday. This is the picture. The 10th drop is, formed pretty well. So it could happen anytime now. So. Okay, so, and this is the longest running lab experiment in the world, so it's still running, obviously. Okay, so in addition to, structural glasses, there are also spin glasses where people put magnetic impurities, magnetic ions like manganese or iron into good metals like copper and gold. And at low enough temperatures, because they are randomly placed in a material, these spins, get frozen. They cannot really move because each spin interacts with all the other spins, and they don't know which way to point. Maybe one pair prefers them to point this way, another the other way. So in other words, there is a frustration in the system, and people usually illustrate frustration by, showing the example of 3 spins on a triangular lattice. If they interact with the antiferromagnetic interaction, in other words, spins prefer to point in the opposite direction. So you can place 2 spins, but what is the third one going to do? So the thing is, the system is frustrated. So obviously these materials have the microscopic picture is very different. They're very different materials, but phenomenologically they behave in the same way. And why is that? Well, this was a big problem for a long time. And it turns out that what all glasses have in common is frustration. So in other words, there is no there is the free energy landscape is, they say rugged. It has many metastable states with similar energy. So each metastable state corresponds to a particular configuration of the system. And so to go from one metastable state to another, the system needs to rearrange collectively. You have to get into another configuration. And these metastable states are separated by barriers with a wide distribution of heights and therefore relaxation times. So on experimental timescales, the system can probe only a relatively small number of such states. So it cannot explore all the states that are available, and this is why it is not ergodic. So understanding, the theoretical description of glasses was a very difficult problem for a long time, I think for several decades. And finally, the theoretical mathematical formalism was formulated in the context of spin glasses by Giorgio Parisi. And in this picture, these metastable states have this tree-like hierarchical structure. And so later, that formalism had a very big impact on other areas of science beyond physics, on biology, mathematics, neuroscience, machine learning, and this is why he was awarded the Nobel Prize in Physics. Okay, so we are interested in electrons. What about electrons? Can they also get frustrated? And the answer is yes. So we are interested in systems where kinetic energy is small, so potential energy dominates. And we are trying to keep it simple. So we have only Coulomb interaction. So if we had only Coulomb interaction, it would favor a uniform density of electrons because they repel each other. But if we have a random potential, this would favor a non-uniform distribution of the electrons. So what do you do when you have both of them present? What are electrons going to do? They don't know. Okay, so they're frustrated. There is no good solution. And it was shown decades ago that this gives rise to exponentially many metastable states with similar free energy, and this was called the Coulomb glass. So this was, found numerically a long time ago, but actually number of experiments has not been, that big. There haven't been that many experiments. There have been some, but not too many. And Coulomb glasses, just like other glasses, are characterized by the so-called dynamical heterogeneity. This is, for example, from the simulations from Vlad Dobrosavljevic's group, where each color represents an electron trajectory. And this is a picture taken over a certain time. So you can see that there are some parts of the sample, the bright areas where electrons basically don't move. On the experimental time scale, the dynamics is very slow. But then in some parts of the sample, they move very fast. So you can see this is heterogeneous. You have fast and slow region, and then as a function of time, these regions also evolve. Fast ones may become slow, and so on. So this is common to all glasses. And as I said, the quantum materials have many competing degrees of freedom. They have complicated phase diagrams, which is why there are so many people studying them. And because of this competition, as I said earlier, one may expect also some glassiness, which indeed has seen in some, various experiments. Here, this is just as an illustration, very old, not a very good resolution STM image. One cuprate where on the insulating side you can see these bright areas are charge distribution. You can see it's inhomogeneous on the nanoscale. And as you get into the superconducting phase, okay, these regions are connected, but it's still inhomogeneous. So you can imagine that there can be many possible arrangements, configurations of these nanoscopic regions that would have similar energy, and you would expect then to have a Coulomb glass. And indeed, actually, some years ago, we did look at one of the cuprates, and we found evidence for charge glassiness in addition to spin glass behavior, but I will not talk about that today. Let me move on. So we want to keep things simple. So coming back to this more recent work, this is an area that a lot of people have been working on in the last 15 or 20 years. So the question is, what happens in quantum many-body systems that are well isolated from the environment if you prepare them far from equilibrium? So since they're isolated, they evolve with time due to their intrinsic, quantum dynamics. So the question is, do they reach thermal equilibrium at infinitely long time or not? So most systems do reach thermal equilibrium, and this is because different parts of the sample can exchange heat and particles, and eventually they reach thermal equilibrium. Their properties are described by standard equilibrium statistical mechanics. However, in this process of thermalization, the quantum information that was encoded in the initial state is lost with time. So there has been a lot of interest in recent years to try to find processes that break this ergodicity so that you can retain this quantum information for some time. This is obviously important for quantum memory. So in addition to being a fundamental question, it has been of interest in quantum information science. And indeed, several such systems or processes have been identified, but the only known robust mechanism for thermalization to break is the so-called many-body localization. And this is a sketch of trying to help people to understand the difference. So here at the top, we have a box with a partition with two different types of particles. Okay, eventually we'll get there. Okay. And when we remove the partition in an ergodic system, these particles will mix, and eventually the density will be uniform. But in case of many-body localization, they will not mix, and you can see you will retain the memory of the initial state. So this is a simple illustration, but this many-body localization was developed really as an extension of the well-known Anderson localization for single particles that move in the presence of strong disorder to interacting systems. Because in Anderson localization, the electron wave functions are exponentially localized in space. So at zero temperature, there is no transport of particles of energy, so such a system is non-ergodic. So the question was, if we add some interactions, can this property of non-ergodicity be retained? And theoretical work did show that for sufficiently short-range interactions, this now called many-body localization can persist even up to some finite temperature. And also what one needs is a sufficiently strong disorder above some critical value. So the important thing to remember is that this is a phase transition in the dynamics of the system. In other words, if you take the system far from equilibrium, for example, by performing a quantum quench experiment, where you change instantaneously a parameter of the system, then the system that is in an MBL phase cannot reach equilibrium. So as I said, this has been a subject of a lot of studies, but there are some key questions that remain, especially regarding the stability and the existence of this MBL phase and the role of dimensionality. It was accepted for a while, at least, that MBL can exist in one-dimensional systems, but not in 2D or higher dimensional systems, or 2D was under debate. But also more recently, the existence of MBL in one-dimensional systems has been challenged theoretically. It seems that maybe it does not exist. However, when theorists talk about existing or not existing, they're thinking about an infinitely large system at infinitely long times. So it is now actually, I think there is a consensus in the field that even if the true MBL phase does not exist, there is a so-called pre-thermal regime in which, even though the system does eventually thermalize on short enough timescales, on experimental timescales, it can exhibit the dynamics, this is annoying, the dynamics of a true MBL phase. Oh. Okay, maybe it's this cable. Okay, I don't know. I'll keep touching things. Okay, so the question of two dimensions has been under debate. The other thing that has been under debate is the precise effect of the range of the interactions. There have been many theoretical studies and a debate, but not enough experiments to actually show what is the range of the interactions, how short range does short range need to be. And also most recently, the important question is how do how do precisely the dynamics of glasses and many-body localization differ? So these are the questions that we wanted to address. We wanted to look at a 2D system, the effect of the range of the interaction, and explore the differences between glassiness and MBL. So experimentally, MBL has been reported in several synthetic many-body systems that are all shown here. Most of them have been 1D, but there has been also some work on 2D systems, especially in these ultracold atoms in optical lattices, both bosonic and fermionic. So in this first experiment shown here, they prepared their 2D lattice of atoms, and then at time equals 0, they remove atoms from one side of the sample, say from the right side. And they can measure the imbalance between left and right. Okay, so this is what is plotted here, this asymmetry, the imbalance as a function of time. So for 0 disorder, which corresponds to these green symbols, you can see imbalance drops to 0 very quickly, so the density becomes uniform very quickly, just like in that box, in a box, with different particles, this simple, model or sketch that I showed you. However, as you increase the disorder, you can see above some critical value, this imbalance persists for a long time, and this was taken as evidence of many-body localization. So, however, if you wait, even longer, it turns out that, even this system thermalizes, and the reason for that is that, the system is not perfectly isolated from the world. There is still some residual coupling to the environment. And in the experiment, these people also actually try to increase the coupling to the environment. And then you expect that the MBL will break down faster, the system will thermalize faster, and this is indeed what they observed. So it is really this very strong sensitivity of this MBL system to coupling to a thermal bath that is a key experimental signature of MBL, in contrast to glassy systems that are robust to that. Okay, so we're limited, or they're limited by time scales. Typically the largest thermalization time is a millisecond, so you need to use experimental probes that can, probe shorter time scales. But also these systems are relatively small. The largest one has maybe 10,000 atoms, but typically they're smaller. And as I said, the theoretical calculations are done in a thermodynamic limit for infinitely many particles. So the interpretation of many experiments, and especially of many simulations, has been a challenge because of these finite size effects. So this is why it is desirable to be able to study these phenomena in electronic systems, because they're much bigger, much closer to thermodynamic limits. And also in theory, the power law interactions have been of special interest, when they're looking at the effect of the range of the interactions. And this is typically what we have in solid-state systems. So this is all very nice. However, studying MBL in electronic systems has been a challenge, because electrons are generally very strongly coupled to phonons, to the vibrations of the lattice. In other words, it is extremely difficult to isolate electrons from the rest of the world. So there have been some attempts, but it turns out that our work is actually, I think, the first successful attempt to observe this in an electronic system. And so we went to the really simple system, and this is a 2D electron system in silicon metal oxide semiconductor field effect transistors, where 2D layer of electrons is formed at sufficiently low temperatures on the silicon side, silicon dioxide interface. And this is the basis of the silicon technology. So this is the advantage of that is that the device properties are well understood, the technology is well developed, and this is also for a system in which the 2D behavior of electrons was reported almost 60 years ago by this gentleman in this paper, and Phil Stiles was actually my PhD advisor here at Brown. He left IBM in the 70s. I think he came here in the 70s. But he maintained ties with IBM, and I actually work, both with Frank Fang and Alan Fowler, and I joined later Alan at IBM in his group. So anyway, this was all fun. But this system is actually perfect for this purpose. Why? Okay, so first of all, this is a capacitor, metal oxide, 2D layers form another capacitor plate. We can change the carrier density by a large amount simply by changing the voltage on the gates. And this can be done very quickly. In our case, the longest time is 5 nanoseconds. Typically, it's the order of picoseconds. And in other words, within our experimental measurement resolution, this is an instantaneous process, okay? Now, these electrons also feel a random potential, which is due to these positively charged sodium ions that are randomly distributed in the oxide. So they're spatially separated from the electrons. They're frozen at low temperatures of interest. So all we care about is really that we have this random potential. So we have a cool interaction, a random potential, and for MBL, this is a well-known fact in silicon that at low enough temperatures, the electron-phonon coupling is negligible. This is what we need, for MBL. So this is an ideal system, and so the heat transfer from the 2D layer is really through these contacts that are labeled source and drain, and up the leads in your cryostat, the wires. And if you put all this in vacuum, then you reduce the coupling to the rest of the world even further. So this is what we did, unless I tell you otherwise. And okay, so as I said, we can perform this quantum quench protocol. We can instantaneously change the carrier density. We can change it by a large amount, so we can take the system very far from equilibrium. And we can also perform these measurements systematically for different densities. So we can start from the high density regime where the system is metallic, move on to lower densities where it becomes insulating. And finally, so what we did, we looked at these devices. Oh gosh, the cable, let me try. Do something, okay. So we looked at the devices where the disorder is sufficiently strong. For MBL, we need strong disorder. And we looked at two different sets of devices. Now, the important thing is that they were fabricated at the same time. So all the steps are identical. The only difference is in the thickness of the oxide. And why is this important? Well, because in one case, here, okay, I'm afraid to touch anything anymore. Okay, in one case, on the right side, the gate, which is a metal, was close enough to the 2D layer, so it was able to screen out the long-range part of the Coulomb interaction. So in one set of devices, we have a long-range 1/r Coulomb interaction. In another one, we have a dipolar interaction. So everything else is identical. Therefore, if we see any differences in the behavior, it must be due to the difference in the range of the interaction. Okay, so before I describe the dynamics, I will have to say just something briefly about the equilibrium or ground state properties. I don't have time to discuss this, so I will just, I don't have time to show you the data, so I will just show you a sketch of the phase diagram as a function of temperature and the carrier density. And everything that we are interested in takes place at low densities where the effects of disorder dominate, where there is a lot of scattering. So we don't have a good metal here. So basically what we found is from the temperature dependence that at low densities in the zero temperature limit, conductivity is 0, which is the definition of an insulator. Above some critical density, the conductivity in the zero temperature limit is finite, which is a definition of metal. Now, in this case, conductivity is small. It has this peculiar so-called non-Fermi liquid temperature dependence, which means we cannot be described by standard quasi-particle picture. So we have a transition from an insulator to this kind of bad metal or a bad conductor. Okay, so we are working in this range of densities because here, for our purpose, there is nothing interesting in the dynamics. Actually, nothing happens, at least on the time scales we measure. So I have time only to describe one experimental protocol and show you the effect of the range of the interactions on that. So the protocol is very simple. We'll start with a long-range case. Basically, we cool the system down to measurement temperature at some high density where the system is metallic, where nothing interesting happens. And then at time equals 0, we reduce the density, the gate voltage, instantaneously. And we track the evolution of conductivity with time. So you can see that the conductivity at time equals 0 drops because we reduce the number of carriers, but it doesn't stop at this reddish line, which is the equilibrium value. Oh, it overshoots it in this case by more than an order of magnitude. And then at much later time, several hours, know the time scales, it approaches this dashed line. And we check that when we warm the system up and cool it back down again, we get the same value, so we know we waited long enough, okay? So we're calling this the equilibrium conductivity. So you can repeat this measurement at different temperatures, and you get a bunch of curves that are shown here. So basically, you can see, all right, so here we are plotting this conductivity normalized by the equilibrium conductivity for each temperature. In other words, on this log scale, 0 is the equilibrium conductivity for each of these curves. So you can see as you wait, the conductivity goes away from equilibrium, then it goes through this minimum, and then at a later time it approaches the equilibrium. At lower temperatures, this process is slower and slower, and it turns out that you can actually collapse all of these curves before the minimum on the same function, which is a product of a power law and the stretch exponential, and in the 0 temperature limit, this is reduced to a pure power law. In other words, there is no characteristic time scale. You have power law relaxation, and all of these are typically found in glasses. It means we have a very broad distribution of characteristic relaxation times in the system. And I think it's interesting that exactly the same kind of this kind of time dependence was found in spin glasses above the spin glass transition temperature. So this is what happens, immediately after at intermediate times. Now let's look at the approach to equilibrium. It turns out that this is a simple exponential process. So you can extract your characteristic. There is one characteristic time. You can extract it, and you can determine its temperature dependence. So in other words, in the 0 temperature limit, we find that this time diverges. So strictly speaking, the system cannot equilibrate only at 0 temperature. It can at all finite temperatures. However, if you calculate the numbers from here, we get at 1 Kelvin, for example, which is not very low temperature, this thermalization time is several orders of magnitude longer than the age of the universe. So for all practical purposes, the system is a glass. Okay, so we probed, this glassiness using other protocols, demonstrated that it exhibits the behavior similar to other types of glasses. And, cable. All right. So basically we found, this is now a sketch that includes the results on the dynamics. So we found that there is a well-defined density, glass transition density, below which there is a glass transition at 0 temperature at all of these densities. So we have this glassy insulator, and we have this intermediate bed metal glassy phase in this system. Okay, so all the measurements are consistent with each other, and ultimately the reason why this is glassy is because you have frustration due to the presence of a long-range cooling interaction and disorder. So what is the effect of the interaction, of the range of the interaction? Can glassiness survive if the interaction is short range, or do we need really long range interactions? So we repeated exactly the same protocol in a system with a dipolar interaction. And okay, so again, it's the same thing. You reduce the density. You track the evolution. This is the blow-up of conductivity with time. You see it takes hours for this to reach this thermal equilibrium. And I forgot to mention before that this protocol is really a large perturbation. So we are preparing a system very far from equilibrium. Okay, so I want to compare the two cases. And so on the left side, we have, again, the glassy case. The data are just taken at a different density. And this is what I told you before. You see this. The system goes away from equilibrium, back up. And then in the short-range case, this is what we get for basically the same density. Now, I think even if you don't know anything about what these figures show, you can see that qualitatively they look different. First of all, if you look at intermediate times, we see that apart from the noise, there is basically, the relaxation is negligible. The system doesn't do much, which is what you expect in the case of MBL. So we don't see any evidence of glassiness here. But the most striking, I think, difference is what happens at long times. Here I showed you that this, and you can see from the data, as you reduce the temperature, it takes much longer, to reach thermal equilibrium. But here, all of these curves seem to reach equilibrium at roughly the same time. And we analyzed, we extracted, this is also an exponential, simple exponential process, so we extracted these thermalization times for different densities and temperatures, and basically found no systematic dependence. Instead, all of the results are scattered around the time of about 10,000 seconds. Okay, so we have very slow dynamics. Does not seem to be glassy. And, what is it? We recall that the system is well isolated from the environment. We also recall that MBL should be strongly sensitive to coupling to the environment. Now, we could not reduce it further, but just like in this other experiment, we could make it stronger. So we repeated some of our measurements now with sample not in vacuum, but in helium vapor. And we saw that the equilibration time is reduced by an order of magnitude, which is exactly what you expect in MBL case. So these measurements were done at temperatures below about 2 Kelvin, where electron-phonon coupling is negligible. We also repeated some measurements at higher temperatures where coupling to phonons dominates, and we found that the thermalization time is reduced by at least another order of magnitude. It didn't really matter where the sample was placed, because all the cooling, heat transfer is really dominated by phonons. So this very strong dependence of thermalization time on the coupling to the environment is really a characteristic of MBL dynamics, again, in contrast to what is expected and observed in glassy systems, where in our experiment, for example, we did not see any change in the glassy dynamics even at higher temperatures. So basically what this experiment showed, I didn't mention or stress this earlier, but these DC transport properties or ground state properties are the same in both cases. In the case of long-range and short-range interaction. But instead, there is a huge difference in the dynamics of the system. So it's so in the case of 1/R, we see that the system does thermalize, even though it may take, more than the age of the universe. And then in this case of dipolar interaction, glassiness does not survive, but we see this evidence for pre-thermal behavior. At this point, I do want to acknowledge people who are actually responsible for these data, especially Lily Stanley, who was a graduate student and who did an, I think, outstanding job. And so this work addressed really one case that was under debate in theory. The dimensionality. So there was a debate whether MBL can persist or not in this case. So our data seem to show that there is no true MBL phase, but we also recall, okay, we still have some coupling to the environment. Maybe if we could make it go to zero, maybe thermalization time would diverge, but I guess we'll never know, just like in the case of glass transition. So to me, this is more like an academic question, but anyway. So, okay, so let me compare quickly what we found to the early experiment on ultra-cold atoms in optical lattices. They measured the density of atoms. So this was an insulating system, no conduction. We measured conductivity, but we cannot measure the density. So you would expect that in case of MBL, it would take also a long time for the density to thermalize. Remember that, those particles in a box. Now, since this is a capacitor, the total density, changes instantaneously and cannot change anymore because we do not change the gate voltage. However, that does not necessarily imply that electrons are thermalized, because you can imagine that locally, they're not thermalized, and there are local changes, and we expect that if this is the case, then this would have a big effect on the conductivity. There will be large noise. And indeed, these are examples of the data. See, you should never let data like this discourage you. In the insulating regime, everything is dominated by this huge noise. So, this is consistent with the existence of local density rearrangements, but in this kind of a device, we cannot probe this locally. We do not have other probes because of the gate, but it would be ideal to be able to have some local probe like STM to see what happens with the density locally. So basically, okay, what I showed you that, this is a wonderful system in the regime at low densities where, this order dominates. The dynamics is always slow. In the case of a long-range cooling interaction, it is glassy, but glassiness does not survive if you reduce the range of the interaction, but instead we see this pre-thermal or MBL regime. So basically this establishes, this system as a new solid-state platform for studies of thermalization in large systems, which is what was needed. And so now, having this system, we can address other open questions, that are currently of interest, in particular, the more detailed differences between glasses and MBL. For example, there are some theoretical models that predict some similarities to glasses, such as these things that I mentioned earlier, broad distribution of relaxation time, some kind of hierarchy of time scales, these dynamical heterogeneities. So to address these finer features, finer points, you want to really probe the correlations, the evolution of correlations in the system. And the way to do that, in our case, because we measure transport, is to measure the resistance noise. And okay, so maybe I take a minute to do that. I will not show you because these data, because it's too technical, too detailed. I just want to tell you that this is a powerful probe for studying correlations. And in fact, this was very demonstrated a long time ago in Mike Weissman's beautiful experiments on spin glasses, where he demonstrated the behavior by looking at higher order statistics. You can actually differentiate between different theoretical models that were proposed at that time, and his data confirmed this hierarchical picture that was proposed by Parisi. And then some years later, we actually looked at the noise in this Coulomb glass case with the long-range Coulomb interaction. These are actually some of our data. You can see that the noise, relative fluctuation of conductivity are of the order of 100%. So from this, you can actually extract a lot of information about correlations, and we found behavior very, very similar to what was found in spin glasses, again, consistent with this hierarchical picture. So we have, some unpublished data on noise in the case of a short-range interaction. The reason why they're not published yet, we are waiting for our theory collaborators. And so this is just a summary of the differences, between a glassy case and MBL. I talked about this top part. The part that I will not talk about is, we studied these fluctuations obtained after cooling with a fixed carrier density. So the key difference is found in higher order statistics. In the case of MBL, we do not see this kind of behavior. It is consistent with this hierarchical picture. So that's the difference, between MBL and glasses. Okay, so to conclude, I'm hoping I convinced you that this system is an excellent platform for studies of non-equilibrium dynamics in large systems. It is definitely simpler than many other materials where you have magnetic effects, structural, and so on. We are now exploring, actually, we are working now using other protocols to explore further the differences between MBL and glassiness. And we are also varying the disorder, but in this kind of device, this is very limited. So what we really want to do is move on to systems that are more tunable. And thanks to the FSU Quantum Initiative, everybody has a quantum initiative of some kind, we are able to now start work, in collaboration with Zhengguang Lu, who's just recently, hired at FSU, to perform similar studies in materials that are more tunable, in particular those based on graphene, TMDs, including MORED devices, because there you can tune the disorder and correlations. You can use screening, to a much larger extent. And we can address questions that are open actually even for equilibrium or ground state properties. For example, the case of strong disorder and strong correlations is not understood even theoretically. I don't know if there are any experiments. I mean, this is an open question. So, this will be really useful for that. And of course, we will also be able to probe non-equilibrium dynamics in the absence of disorder, because all you need is a frustration. And some of these systems have geometric frustration. And so it will be interesting to see whether, through the grapevine, unpublished, there are some STM data somewhere where actually that suggests that, there is some glassiness in some of these structures. So, again, these materials will enable us to use also other probes, for example, magneto-optics, but also local probes such as STM to be able, to compare and correlate with these transport measurements. So I thank you very much for your attention. Yeah, she has to leave. Yeah, I'll see you. Yeah, no problem.
Thanks for the nice talk. I just really wanted to clarify. So when you say MBL has, as opposed to the glassy phase, has a scale in it, what's setting the scale in the MBL phase? What is the physical parameter?
What scale? Oh, no, I said there is no scale. Oh, yeah, there is scale.
Yeah, there is a time scale for MBL, and what is that time scale?
Okay, nobody knows, okay? No, nobody knows. There is one paper by, first author is Artiaco, and, they collaborated with Parisi and so on. They try to come from a glassy picture. They say there is in MBL, there is a length scale for quantum entanglement, like correlation length. So there are there is entanglement over some correlation length. And, that's what they're saying. However, people who are in MBL, they don't want to look at this paper because it's kind of it's too related to glass. Okay, they need to talk to each other, okay? So that's the only paper, and it's relatively recent. And again, I try to talk to different theories, but as I said, people have divided opinions. So I think so that's one possibility, which to me seems very interesting. But the answer is we don't know, and so maybe one day when our theory collaborators are, I wish I had a better answer, but I mean, it's an open question.
Okay, I'll just ask. I was wondering, in glassy systems, often people can see these memory effects that you talked about at the beginning. Are there ways for you to check memory effects in the MBL versus the glassy phase, and would you expect differences?
Yeah, I mean, we're looking at the aging phenomena, which is like a memory. In glasses, older systems are slower, just like we are generally. But in MBL, nobody knows. So some people think maybe it's faster, maybe slower, maybe it doesn't matter. So we are actually, this is what these waiting time experiments are. And then, there are different protocols you can do to see whether a system remembers where it was. So it's essentially the same thing. But yes, we had done that, and we had done it also in other systems like cuprates, which are affected by the magnetic field. These actually, we have not done this in a magnetic field at all. Don't tell anyone, we work on cuprates, they need high magnetic fields, so we do use high magnetic fields. But we actually did some early work in the glassy case in the magnetic field to try to see whether this glassiness is due to charge or spin degrees of freedom. Because we knew from other work that it takes only like 2 or 3 Tesla to fully spin polarize the electronic system. And we saw that this glassiness persists So this tells us that, okay, spin doesn't matter. So we know it's really a charge, Coulomb glass. But yeah, I mean, depending on the system. So in some cuprates, we did use magnetic field, to go up or down. I mean, to basically use different protocols, see if the system remembers. So there are various, history-dependent phenomena, hysteresis. So it depends on your system.
Okay.
Yeah.
Okay, I had another question too. Since you did those, you showed briefly those noise experiments.
Yes.
So you can look at the fluctuations.
Yes.
I was wondering if there's a way you can measure the relevant dynamic susceptibility, and then you could maybe see how fluctuation dissipation is violated in the different systems, and if it's different between.
Well, this was done in spin glasses. People measured AC susceptibility in spin glasses, and
so the fluctuation dissipation is violated.
It is violated, but if the system is not very far from equilibrium, it was the theoretical prediction was confirmed experimentally that FDT can hold, but instead of temperature, now you have an effective temperature.
Yeah.
And,
but in MBL, then maybe very different? Or?
Well, okay, yeah, I mean, yeah, this is very different. I don't think that's, applicable. Here you just need to be in one state, many body state.
Very nice talk. This question is a little bit related to what Aaron asked you, but so in the structural glasses and the spin glasses, it's thermal fluctuations that are providing the sort of the randomness, dynamic randomness, whereas in your electron glass, it's quantum mechanics.
Yes.
And do you see any essential difference between these two forms of?
Actually, no. Because, for example, I showed you the relaxations that you observe. They're the same as in spin glasses, above the spin glass. The noise was the same, qualitatively. So, there is no, we have not observed it. We looked at the aging effects. It was all similar. So I think it's striking. But yes, we have a zero temperature, glass transition, so it's quantum with, everything is more pronounced at lower temperatures. So quantum fluctuation. Because, MBL people often ask me, how do you know quantum mechanics is important? Well, I don't know, we are in the limit of zero temperature, they should be. So that's interesting. I mean, maybe some other features would be different, but these are not, which is why I think glasses are amazing, because again, phenomenology is so similar.
So entanglement may not be playing an essential role.
Well, I think, we haven't done everything we can with this noise. For example, they say in the case of MBL, the noise should be bigger as the system evolves, and this is what we see in the experiment. So I keep thinking, okay, from this noise, as the system approaches equilibrium, we should be able to extract some information about this entanglement, but I don't know what quantity to look at, and nobody has been able to tell me either. But I just feel like, okay, the information must be buried there. We should be able to get it somehow from the noise. So if you have some suggestion, anyone, let me know. We have a small, the tiny range of systems. We check that, yeah. And somebody also suggested, okay, the width of the contacts, or, how big they are, because, okay, there is more heat transfer. Again, we don't have enough to, to be able to say anything.
Can you run so you saw this stretched exponential relaxation.
Yes.
That's similar to spin glasses, but is the actual stretching parameter the same, like this beta term?
I think they're very similar. And in our case, this stretch term actually, that vanishes in the zero temperature limit. But you can see they're small. It's 0.4, and it depends on density. So this is the range, depending on density. This is the stretch one.
And then in spin glasses, that's typically...
this is typically what people get.
And it just means you have a distribution of relaxation.
Yes, But in our case, I think this is cool. It's just a power law in the zero temperature limit. But yes, it's similar.
Any other questions? Okay. Well, thanks for a wonderful talk.
Okay.